moduli space. So unfolding means so it means connecting regular singular connections and irregular singular connections. For constructing a modular space which connecting regular singular and irregular singular connections, it is necessary to control the data of local exponents. The local exponents means the data of eigenvalues of the connection, residue of the connection in the regular singular case. And the data of, giving the data of eigenvalues is equivalent to giving GLRC adjoint orbit of diagonal matrix. So I will start with a small remark on adjoint orbit from elementary linear algebra. On GLRC adjoint orbit. This is rather an elementary theory, elementary content. So let us fix distinct complex numbers, and let V be a vector space, complex vector space, which has dimension R. And we set a set of linear maps from V to V, linear endomorphism. Which has eigenvalues mu1 mu r. So set of endomorphisms having the eigenvalues of the prescribed eigenvalues. So this is isomorphic to the GRC adjoint orbit, joint orbit of the diagonal matrix. This is just an elementary linear algebra. And for this adjoint orbit, we have the following lemma. For each endomorphism in this adjoint orbit, there exists an isomorphism theta from the dual vector space of V. This is isomorphism, linear isom. V dual, this is a dual of V, and there is also a linear map from V to V dual. This may not be isomorphic, such that the given linear endomorphism is a composition of theta and kappa, and theta transpose. This means that dual of theta. So taking the dual theta transpose is linear map from V dual to V, and it satisfies it coincides with theta, and kappa transpose also coincides with kappa. We can take these data. And furthermore, theta kappa is unique modulo the action of CT over the polynomial ring divided by the ideal generated by the eigenpolynomial, and it's the group of invertible elements of this ring via theta kappa. Suppose inverse kappa for yeah. We can for each element in the adjoint orbit, we can factor the linear map as theta and by theta and kappa satisfying like this symmetric property. And theta kappa is unique up to this action. And I don't give a precise proof, but give an idea of constructing theta and kappa. Idea of proof. Since F acts on this vector space, V has natural module structure over the polynomial ring by regarding the action of T as the linear map F, linear endomorphism F. So there is an isomorphism from this ring to the vector space V with the action of polynomial ring by regarding the action of T as the endomorphism F. This is elementary linear algebra part. And similarly, V dual has the endomorphism F transpose, and there is also an isomorphism of this ring to the dual vector space. This is the same thing, and we define theta small t. Sorry. This is large t. Thank you. Okay, this is large t. And there is an isomorphism from which makes the dial commutative, and we take kappa to be theta inverse composed by F, and we can check the symmetric property of theta and kappa by routine calculus. And we get this lemma. So by using this lemma, the set of the adjoint orbit can be parameterized by theta kappa, the data of theta kappa modulo the action of the commutative algebraic group. And from this idea, we can describe the tangent space of the adjoint orbit using this idea. So we set SV dual transpose tau, and and SV VDR. This is a homomorphism. The set of homomorphism are linear maps from V to VDR satisfying symmetric property. Yeah, yes. Unfolding case. Today I don't consider nilpotent like. But this Lemma we can easily extend nilpotent like map. So by replacing the condition that f has minimal polynomial of degree r, fixed minimal polynomial of degree r. But today I restrict the simple case. Unfolding means I will explain later, but irregular singular connection means connection admitting pole along multiple divisor with multiple components. And the regular singular means that the divisor is a reduced divisor. Yeah. Nilpotent like but for the connection, there is a theory of formal connection, and in general, we should take a ramified cover, and for that covering, we can decompose the eigenvalue decomposition. So the theory is rather complicated. So today I focus on simple case. And yeah, I said this. Please. Then we have the following proposition. The tangent space of the tangent space UR at F of the adjoint orbit at the point theta kappa is chosen by this lemma is that tangent space is isomorphic to the first cohomology of the following complex H1 of Ct over determinant T minus F V dr plus V dr T minus F. Here, this map is defined by Pt goes to what is this theta composed with substituting the F transpose in the polynomial P, and here is theta P minus of Pf transpose composed with kappa. The first map is divided by this, and the second map is given by tau xi goes to theta tau kappa plus theta xi, where theta tau kappa plus theta xi. This is defined by trace of tau kappa plus theta xi composed with pf. pt in polynomial. So, the kernel of this map is the parameterizing the tangent space of the data of theta kappa in this lemma, and the image of this first map is the tangent of this action of this commutative group. So we can obtain this description of the tangent space. And using this expression, we can give an expression of the Kirillov constant symplectic form, which is a well-known symplectic structure on the adjoint orbit. So Kirillov constant symplectic form the adjoint orbit is this is a very known symplectic form on the adjoint orbit, and this is given by tau xi, tau xi and tau prime xi prime goes to half of the trace of tau xi prime minus tau prime xi. I think this is, I don't remember the sign, but yes, this is okay. So, this is a small remark on the adjoint orbit. And using this idea, I will give a parameterization of connection. So, we go to definition of new mu connection and their moduli. I will restrict to a very simple case today, but the theory should be generalized, should be more generalized setting. But today I will restrict to a very simple case. So let C be a flat family, algebraic flat family of smooth projective curves over a fine curve. B. And we assume the existence of unfolding equation of the divisor. So there is this is an algebraic function, epsilon, and affine open subset. Open. And more assume there is a algebraic function on the affine open subset Y, such that the zero locus of this equation, this is not good, such that di, which is the zero locus of this equation, this is contained in C, but this is Zariski closed subset. So this becomes a Cartier divisor. And we further assume that DI are all distinct. Yeah. Then we put D to be the sum of these divisors. This sorry. I moves from 1 to n, and this becomes a divisor on C. So if epsilon is 0, the divisor di becomes a multiple divisor, and if epsilon is not 0, the divisor di becomes a reduced divisor. So we regard this data as C and D as data of unfolding data. So we consider a connection over this C. Mu only fixed mu is no relation. Just take fixed complex number, reference complex numbers, and yeah. So we fix mu such that mu k, mu1 and mu r are mutually distinct. This data mu is only data for reference distinct complex number. And now I will prepare the data of local exponents. First, I take a tuple of complex numbers. This data is nothing but the data of residue part. I moves from I moves from 1 to n, and k moves from 1 to r. So take lambda, which should be a data of residue part, and which satisfying that all sum of lambda ik is integer, and we set a as the minus of the summation of lambda ik. And we consider polynomial nu t, cr minus 1 tr minus 1 plus data plus c1 t plus c0. This is a polynomial over OD. OD is the structure sheaf of the divisor D. So coefficient in this OD such that new, sorry, too strong. If we write new IT by restriction of new t to the divisor di by new it, this satisfies the residue condition. So residue of summation of di B is each point in B, and the residue at P of nu I mu k. Substituting the fixed complex number mu k in this polynomial, and we take we consider this differential form and taking the residue at each point P and take summation. And this becomes lambda ik for any ik. So we regard these data mu I mu k as the set of local exponents, and which satisfy that the summation of the residue around di is lambda ik, the fixed lambda ik. I should assume more assumption. Moreover, we assume that mu I mu 1 p mu I mu r, these are distinct at any point in di. Yeah, and we regard this data nu t as the set of data of local exponents for the connection. I don't define the connection, but we regard it as nu t as the set data of local exponents. And we go to the definition of the new mu connection. Nabla n is a new mu connection. If first E is an algebraic vector bundle of rank R, algebraic vector bundle on certain fiber of this family of curves of rank R, and degree A. So for some point B on some fiber, and nabla is a connection on this vector bundle CB. This is an algebraic connection. And thirdly, N is an endomorphism of ED. Morphism such that restriction of N to each point has the eigenvalues mu1 mu r at any point p in dB, and I write in the above, left above. And nabla restricted to the divisor di is equal to the substitution of the endomorphism ni to the polynomial ui times this differential form. This is the definition of new mu connection. So there is some remark. If epsilon b equals 0, then this part becomes like irregular singularity, and new mu connection is an irregular singular connection. And if epsilon is non-zero, new mu connection is regular singular. This part becomes this differential form has only simple pole, and this is a regular singular connection. Regular singular connection. And I don't give a precise definition of the stability, but we can define stability, alpha stability, by using the induced K-psi parabolic structure. On the bundle with connection. Parabolic structure with respect to subweight alpha. Then we can define the moduli space of new mu connections. B is moving around there, so these data over all these. So this is false for any B. Yeah, any B. Sorry. I write the theorem, but this is almost no known facts, but there exists a moduli space of mu connection. With mu connections. And which is smooth and quasi-projective morphism. And the fiber alpha nu b mu over b over point b has dimension 2r square g minus 1. Sorry, g is the genus of the fiber of the curve C. G equal genus of fiber. And moreover, we can express the B relative symplectic form, on this family of modular space via the idea from section 1, easy observation on the adjoint orbit. I don't write precisely, but modifying the expression of the Kinnov constant symplectic form, we can obtain relative symplectic form on this family of modular spaces. Yes, epsilon 0, 0. It is continuous. Modular space is continuous. Yeah. Over epsilon. Yeah. But the problem is the connecting the general isomorphic deformation, and that is not completed yet. So I will explain from now. But before going to general isomorphic deformation for irregular singular case, it is rather classically well known concept, and which is described as the Jinbo-Miwa-Ueno equation in the famous paper. But there is an unfolding theory by Fruitbis, Lambert, and Rousseau. This is a very hard theory. And I briefly give a part of the idea in the theory. I only explain an introductory part, but anyway. So let delta be unit disk in the complex plane, and D be a divisor defined by this equation in delta cross delta. And consider the differential equation given by dc over dt equal e exponential of root minus 1 theta the m to the power minus epsilon m. Where theta is some fixed real number. Then we can observe that for each p delta times delta minus t, which is close to t and satisfying epsilon of epsilon component of that point is sufficiently small, there exists a solution of this equation. Z theta t solution of this equation star satisfying the initial condition and z theta t. The solution of this equation is something like a flow of some certain vector field, and taking t go to plus infinity, this is converged. Sorry. For a close to and sorry, we should take certain theta and z theta t, and this is accumulated in this device. So a statement means that for a point close to the divisor d, we can choose a certain angle theta, and then the solution of this equation is convergent to the point in D. Using this solution or flow of the vector, certain vector field, Fruitbise, Lambert, and Rousseau obtain solution of certain differential equation. So consider linear differential equation. dy equal a dz over cm minus epsilon y, where A is a holomorphic a matrix of holomorphic function and satisfies a restriction of A to D is like U1 data mean UR with U1 P, UR P, and is distinct. Consider the linear differential equation. So this is something like local new mu connection, which is something like local new mu connection. It is distinct at any point in D. And theorem. this theorem is essentially a consequence of classical Levinson's theorem, but mechanism of using Levinson's theorem is given by these three people. So I omitted. There exists a solution of the differential equation. The differential equation satisfying limit of solution of the linear differential equation in the neighborhood of the flow such that y theta p times exponential of minus of u1 nu r dc over cm minus c epsilon. This is convergent, and in their paper, the limit is given by some constant diagonal matrix, but replacing the solution by acting inverse of the diagonal matrix, we can obtain the limit is identity matrix. This is somehow the key point, key theorem in the for defining generalized unfolded Stokes matrix. So the idea by Ludwig Lambert and Rousseau is that they regard this matrix. If we choose another theta prime or p prime, we get another equation of the linear differential equation. And if we take y theta p inverse times y theta prime p prime, because these both satisfy the same differential equation, this is a constant matrix, constant in Z, and they regard it as unfolded Stokes matrix. Unfolded Stokes matrix. For the case of epsilon is 0, this is nothing but usual Stokes data, Stokes matrix for irregular singular case. And for the case of irregular singular case, generalized isomorphic deformation means that deformation preserve the Stokes matrix constant. So we want. And for irregular singular case, generalized isomorphic deformation is well known, such as Jinbo-Miya-Ueno theory. And we can construct it on the in our modular space. But for unfolded case, I don't succeeded yet for constructing the generalized isomorphic deformation. So I will explain the idea of getting generalized isomorphic deformation for irregular singular case. That is almost well known, especially for the P1 case. It is written in the paper by Jinbo-Miya and Ueno. Generalized isomorphic deformation. For irregular singular fiber. singular fiber. This part is joint work with Professor Masahiko Saito. So we assume epsilon b equals 0, and set mu lambda to be this is a space parameterizing the local exponents, satisfying certain conditions, such as compatibility with the residue, the given residue lambda k, and so on. And we can consider a relative moduli space B nu bt is in this space, and m alpha nu b mu. This is a family of moduli spaces over T mu lambda. So the fiber is the moduli space of nu b mu connections, and nu are moving in this space, and we regard this space as the space of time variables. And idea of constructing the general isomorphic deformation is very similar to the construction of the usual isomorphic deformation for regular singular case, which I explained in the first talk. So we want to construct splitting of the tangent map. Splitting of the tangent map. Tangent map is tangent map from a surjection from this tangent bundle to this tangent bundle. This is that's usual tangent map. Such that the image of this tangent map of tangent bundle by D becomes a subbundle satisfying certain integrability condition and define foliation. That which means that Stokes matrix are constant with respect to the moduli parameter. And I will briefly give an idea of constructing this homomorphism D. So let E tilde double N tilde be a universal family. On the moduli space over some over an eternal piece of the moduli space, and take tangent vector field, V over some t mu lambda t for some for Zariski open subset. No. T mu lambda Zariski open. Then V corresponds to first order deformation of the polynomial nu. V corresponds to nu t plus nu prime, t bar nu prime, where t bar is first order deformation parameter. And nu t here, nu t means data over universal data of t prime over local exponents over t prime. Universal. Universal family of the data of local exponents. And we write, we put m cross t mu lambda t prime, and we want, similar to the first talk, we want to construct a horizontal lift EV, Nabla V, LV over this universal family, universal family, and restricted CB times M prime. Then, if we obtain, I don't give a precise definition of the horizontal lift because I explained in first talk. So, and if we get the horizontal lift of this universal relative connection, we can get tangent vector field over the modular space and get the splitting D. And I will give an idea of giving a local horizontal lift for this relative connection. So, universal family of relative connection can be described like connection matrix over trivial bundle omega 1 CB UI B times T prime over T prime DI cross T prime. There is restriction of the universal family. So this is UIB times M prime and UIB times M prime. Precisely speaking, we should pull back this differential form over M prime and take it as. And over trivial bundle connection is given by a connection matrix like this. Here we assume epsilon is 0. So now this part becomes Zi, mth power of Zi, and connection matrix is given by this. And we may assume A restricted to some power of divisor di times m prime. This becomes diagonal matrix new mu1 new mu r. Right. Then so we can take a matrix of endomorphism my minus 1. Mi minus 1. So I will such that I will write in the left board. That B is equal to di prime m prime is given by the following matrix: new prime of mu1 ci y dci, new prime mu r ci mi restricted di cross m prime 2 of we can take rational difference matrix of rational differential rational function with like this satisfying this type. And I remark that in the integration there is no residue part. Because in the parameterizing of the space of local exponents, we fix the residue part lambda. So new prime, through part of new prime, deformation new prime part becomes 0. So there is no log term in this integration. So this becomes we can take B as a rational differential form, the rational function matrix of rational functions. And then if we put dB plus bracket of AB dzi, and we put and for some preparation of notation. And M prime, this is just M prime times T prime V. If we put, we can define total connection. We can define total connection W UI P. This is a connection on this space prime V to this space prime V tensor of omega 1. Here should be careful. Prime T prime V over T prime. T prime V is scheme over T prime by this morphism. So it is something twisted differential form, and d I b times T prime V given by F1 delta Fr goes to Fr dFr plus A plus T bar C divided by GIMI plus B dt. And which is and this is integrable connection. And we can put gluing them. We obtain horizontal global horizontal lift. EV, nabla V, NV, and tangent vector. By taking the induced relative connection, we get tangent vector in the modular space. Then we can define the splitting of the tangent bundle T mu lambda. So by construction, this morphism, homomorphism D is algebraic homomorphism of vector bundles, and determine the foliation, which means that the Stokes matrix constant with respect to the moduli parameter. So that is the story for irregular singular case. But for unfolded case, there is some difficulty taking such PAs. So usually integration becomes a multivariate function. And I want to control the multivariate function which behaves well. But I don't succeed for the local lifting yet. So this is my story. Oh, thank you for listening.
You choose the deformation of the singular point as a m per multiple point, m per multiple point to the m point of the simple point.
Yes.
G m g to the
yes.
But you may use some other curve with the g and the epsilon equation like some so.
So I restrict to very special type of unfolding equation.
Yeah. But you may choose another type of the curve.
So
you may formulate a.
I hope the theory of Hurtubis and Lambert-Rousseau in their theory, the setting is more general setting. But for me, it is hard for me to understand all of them, and I restrict the special case.
Thank you.
Okay, I don't see any hands. So let's thank the speaker again.